Hey everybody, welcome to geometry. We already finished the last volume problem. You guys did that with Miss Clark last week, and so we're going to do some analyzing of formulas and then do our introduction to circles. All right, so this is from the last class we had together. So if you're looking for it, it's going to be in those notes from last week. And here we're talking about dilating shapes by this factor. So when you see the word factor, hopefully you're thinking of multiplication. And to do these kinds of problems, your OMHS describes it one way. So I'm going to show you guys another way, a way that a lot of people find to be actually easier. So we're talking about a triangle with area. So we want to remember that the area formula for a triangle is 1/2 base times height. And it's telling us that that is 3 millimeters squared. So when you're looking at dilating a shape, we're going to multiply all the lengths by whatever the factor is. So when you look at the formula we've been given, there are two lengths, right? The base and the height. So we're going to multiply the base by 6, and we're going to multiply the height by 6. We don't really need to know what those numbers are. We just know that we're multiplying each of those lengths by 6. So that means we're going to multiply the entire shape by 36, right? Because 6 times 6 is 36. So we're going to multiply the entire area by 36 to get that factor of 6 dilated. So all you do is you take whatever the area was, 3 millimeters squared, and we're going to multiply it by 36. And you get 108 millimeters squared. So we multiplied the given area, 3, by the total growth factor. Here it's growing because it's bigger than 1, so we know the shape's going to get bigger. And you want to take into account each length that the shape has in the given formula, right? So it was area, so that's why we wrote this area formula. And we found that there are two lengths, the base and the height. So we multiplied the 6 twice. So 6 times 6 is 36. Let's try another one. Here we have a rectangle with that area. So we remember the area formula for a rectangle is length times width. And it's telling us that equals 5/8. I just pulled this right from here. Area of 5/8. So we're going to dilate each of those lengths by 8. I see two lengths, right? The L and the W. So the total shape will be dilated by a factor of 64. So now all we do is we take the original area, 5/8, and multiply it by 64. Get the new area. And when you plug this into your calculator, you will get 40 feet squared. So we're changing the entire shape, but we're just taking into account each of the lengths that the shape has. So let's try another one. Don't forget, at any point, since this is a recording, you can press pause, right? If you need to take any notes or you want to try it on your own, and then you can press play. So here is our prism. Now this one is a little bit tricky because it doesn't tell you what kind of prism it is. Remember, we have two types of prisms here. We have the triangular based prism and we have the rectangular or square based prism. So I don't really love this question because it doesn't tell you what type of prism. Sometimes it won't matter, but I'm just going to choose for us and say, let's do the triangular based prism. So it tells you the prism has a volume of 450. Okay, so let's go to the volume formula. Volume equals big B times H, and that equals 450. And it's going to be dilated by a factor of 2. So that means we're going to multiply every length that's involved in this formula by 2. Well, look at the formula. There's a big B. Do you remember what big B stands for? Remember, that's the area of the base. So this base is a triangle. So that means this big B is 1/2 base times height, right? That's the area of a triangle. So I replaced big B with the area of that base, which is 1/2 base times height. So now look, I see 3 lengths. I see little b times 2, the height from the area, and the height from the volume. So we're really multiplying the entire shape by 8, a factor of 8. So just like the last one, you're going to take the given volume, 450 times 8. And that equals 3,600 feet cubed. We're talking about volume in this one, so it is cubed. All right, this might be a great time for you guys to pause the recording and try this one on your own, and then come back to the recording and check your work. So again, this one says a prism. It doesn't tell you which kind of prism, so I'm just going to choose triangular prism again. You could do either. And here it tells you, this time it tells you the base area. Right, so be careful. This one's not giving you the volume, it's not giving you the area, it's giving you the base area. So remember, the base area in a triangular prism, our base is a triangle, so the area is 1/2 base times height, because that's the area of a triangle. And it's telling us that equals 3 meters squared. And then it tells us the height. So the height of that triangular prism is 4. So that would be 4. And we're going to dilate them by a factor of 3/2. So remember, we're looking for all the lengths involved. So I see little b, that's times 3/2, little h times 3/2, and this h in the height times 3/2. So the entire scale factor is going to be 9. Nope, not 9. It's going to be 27, right? 3 times 3 times 3 is 27. 2 times 2 times 2 is 8. So we're going to multiply the entire shape by 27 over 8. Now in the last examples, it had given us the volume, right? And it had given us the area. This time it doesn't. So let's just find it. It wants to know the volume, so we're going to find the volume of the triangular prism. The original volume is big B times h. Well, big B is 3, and little h is 4. So the original shape's volume is 12 meters cubed. Now remember, to find the new dilated shape's volume, all you do is you take that and multiply it by that total scale factor we found. So 12 times 27 over 8 is 40.5 meters cubed. So it did go up, right, from 12 to 40, and that's because even though this is a fraction, it's still bigger than 1, right? So anytime the number is bigger than 1, the shape is going to grow or dilate, and anytime the number is smaller than 1, it's going to shrink or get smaller. All right, now we're looking at our introduction to circles, and I wanted to show you guys this because it's amazing. So this is an actual park. It's in Philadelphia, and it was designed by James Corner Field Operations, this company, this organization. They actually won a big award for doing it. And landscape architects worked using math and design to create this park. It's so cool. They have different activities in all of the different circles. You can't see those very closely because I couldn't zoom in, but you can see here these might look like tables, and I'm not sure what that is. We'll have to research this a little bit more to see exactly what kind of activities are involved, but I just thought that was really cool. You guys can see geometry being used in everyday life. Like, this is a real person designed this, a real group of people. They got paid to do it, and they won a big award. And if that's not mind-blowing enough, look, it happens all across the world, not just this one park. It happens with water and grass and plants, and these ones are drawings, obviously. But we do have real ones, real diagrams, real pictures of places where this actually occurs. So I just think that's just really cool. So the geometry you're studying right now can literally be applied to this profession to make these places for people to use. Really cool. And if that, again, wasn't enough to convince you, then we're going to look at some problems that are pretty cool with pizza and deciding which size pizza to get, like the best, the most amount of pizza for your money sort of thing. All right, so let's recall the parts of a circle. You guys, I'm sure, can do this in your sleep, right? This middle point here is called the center. The distance all the way across through the center is the diameter. And remember, half of that distance is called the radius. And lastly, we have the circumference. That's going to be the distance all the way around the outside of the circle. So those are some terms you guys learned even probably well before our class. I know we went over it a few weeks ago in our class as well. So we're just going to dig a little deeper. We're going to get to the actual geometry concepts now. So what is an arc? An arc is actually a portion of a circle. So look, we can highlight it. There's an arc. If you were to draw it with your pencil tool, it might look like this, right? So an arc is a portion of the circumference of a circle. Circumference. It's just a part of that outside edge of the circle. You can think of in real life, you know, we have archways or arcs like in architecture, get it? These are like pillars. My drawing's terrible. This could be a bridge. So this is an arc. So let's think about it. When you think of how many degrees are in a circle, how many degrees are total? If we started here and we went all the way around the outside of the circle, we would go from 0 degrees to 360 degrees, right? There are a total of 360 degrees in a circle. Well, if we start at 0 and we go up this far, we have 90 degrees. And we keep going around, we're going to add another 90, right? That's 180 degrees. Remember, half of a circle is 180. Keep on going around, and we're going to add another 90, right? Each of these are 90, so that's 270 degrees. And then you keep going, and that's where you add another 90 to get that 360. So we're going to be looking at arc measures, and we do those in degrees. So there's 3 kinds of arcs we're going to call. We're going to call a minor arc, a major arc, and a semicircle. So a minor arc, the word is kind of cool because it matches its definition. Minor meaning, you know, not so important, not such a big deal. It's small, it's minor. So a minor arc is an arc that is less than 180 degrees. Less than 180 degrees. So if you look at this picture over here, an example would be arc AB, that small little piece right there. And this is how you name an arc. You write the letter where it starts, the letter where it ends, and you put a little baby arc over it. Arc AB. You could also write arc BA. That is fine. It doesn't matter which letter you start at. With minor arcs, you're going to typically use 2 letters. I mean, you could use a 3rd one if you wanted to. There could be like another letter in here, but it's not necessary. It's redundant. So let's look at a major arc. I'm sure you can guess, right? A major arc is an arc that is greater than 180 degrees. So when we name a major arc, you do the same thing. Whatever letter you're starting at and wherever you end. So if I wanted to start at A, I would go arc A, B, C. That one surely looks greater than 180, right? This is the diameter. So arc A, B, C. Now, major arcs are typically identified with 3 letters. Because what if you said, well, I'm going to name this arc AC, A to C. But as a reader, I don't know if you mean that arc or this arc. See, they both go from A to C. The black one is a minor arc, it's smaller. So that's why we use 2 letters for minor arcs and 3 letters for major arcs. It just helps the reader differentiate the two. So if you say arc AC, I know you're talking about this minor arc AC here, this black one, versus this one, AC. So that's why we're going to use that 3rd letter in there, B, to name that major arc. A semicircle is an arc that is equal to 180 degrees. And you guys know that's halfway on the circle, and again, it's kind of up to you. It's kind of also up to what the diagram shows, but we will again typically use the 3 letters with the little arc above it. And I'll draw an example over here. If we had A, B, C. Now this one, it's not as important to use 3 letters because if you said AC and we went this way, it would mean the exact same thing as if you went this way, right? Because they're equal, the 2 halves of the circle. So it's not a huge deal with this, but it is a big deal for the minor arc or the major arcs. And you guys saw why, right? If you don't use the right naming, we won't know exactly which arc you're talking about. So let's label some. Here's a pizza. And again, I'm very visual, so minor arc meaning small. That's that slice of the pizza here. And the major arc would be the rest of that crust, the larger piece, bigger than 180. All right, so let's try some. We're going to identify a minor arc, a major arc, and a semicircle, given that CD is the diameter. So sometimes when you look at a diagram, you're not quite sure whether it's a diameter or not. So usually the instructions will tell you, they'll say, assume CD is a diameter, kind of thing. So from C to D, it goes right through the center of the circle, and that should be a big clue to tell you that that's the 180 degree mark. That's why they cut that circle in half. So there's a lot of different answers for this, right? A minor arc is something that's less than 180. So here's one. You could say C to E. And we know you're talking about a minor arc. What else? We could say EC. There are tons. You could go C to F, anything that's smaller than 180 degrees. So let's do a major arc. We could do E, D, F. Although that appears it might be exactly 180, although we're not sure. We could do CFE. That one's really big, right? So there's a few examples. And then our semicircle, we could do CD, DC, right? From C to D or back again. So did you know an arc actually has 2 measures? This is kind of strange. It has an arc length. So the length is the distance around that part of the circle that it is. It's a length. So it's going to be measured in things like inches and feet and millimeters. It's part of that circumference of the circle. But also, arcs have measures, and arc measures are measured in degrees. So we're talking about the degree measure here. See how it's pointing to that angle? Let me get an angle degree measure here that matches with the corresponding arc. So there's 2 measures that an arc has, the length given in distance and the measure given in degrees. These are just sort of the math terms that we use for those. So central angle. What is a central angle? I love this definition because a central angle is something that's really sort of, the definition comes from the word, right? Central. So the vertex of the angle is coming from the center, and it forms an angle, right? So the definition is an angle whose vertex is on the center of the circle. Is the center. I'm sorry, I don't have a text typing tool on this platform, so sorry about that. Hopefully you can read that. You can, right? It's an angle whose vertex is the center. So we have 3 examples down here below, and if we were in live class, I was going to ask you to give me a green check or red X. You can think about example 1 here. The red lines are forming that angle, and the vertex of that angle is right on the center. So yes, this is a central angle. Example number 2, same, right? The vertex is the center, and the edges go to the outside of the circle. That is a central angle. Number 3 here, you can see that there's an angle formed, but the vertex, it's not on the center of the circle. It's kind of hanging out, it's floating. So this is not a central angle. Number 3 is an example of not a central angle. So central angles are pretty special because, of course, there's a theorem that corresponds. And I wanted to show you guys these pictures and see if you can see what's happening. So the central angle theorem tells us the measure of the arc. Remember, we said that measures of arcs are measured in degrees. So look, number 1 here, it tells us arc, the measure, that little m, means measure of arc AB is 27 degrees. Oh, okay. The measure of arc ABC is 190 degrees. And the measure of AB is 100. Do you guys see what's going on here? I'm going to label. This is 27 degrees. So the arc measure is the same as the angle across from it. See, 27, 27. The measure of ABC is 190. And the angle across from it is 190. This is for central angles. When the angle is right on the center of the circle, the arc across from it is equal to the angle measure. So that's the central angle theorem. When you have a central angle, the arc, it intersects. We use that word intersect. If you look, for example, over here, this angle is intersecting this arc, right? Basically, it means that that angle forms that arc. It makes a piece of the pie. So the central angle of the arc that intersects it are congruent. They are equal. So a lot of people love this theorem because it just makes sense, right? The angle that's formed in the center of the circle is equal to the measure of the arc across from it. So let's try some. Let's try A. Arc ST. Here's S to T. And I knew it was that versus this, right? Because it only had 2 letters. So remember, we used 2 letters to identify minor arcs. So here the angle measure is 80, which means the arc measure is going to be 80, since that's a central angle. So the measure of ST is 80 degrees. Let's try B, the measure of STQ. Let's get another color here. We're talking about this big arc. And you can see we are going to have some angles to add up, right? Because it's going to total the 80 and the 120. So that entire angle is 200, which makes the entire arc 200. So the measure of STQ is 200 degrees. That is a major arc. It's bigger than 180. All right, SR. So it's this little guy down here. Now that one doesn't have an angle measure inside, does it? That's not very nice. It's missing. But how could we find it? I'm guessing you guys know. The entire circle adds up to 360, right? Well, if we already know that these other three angles, then we can just subtract from 360 to see what's left. 120 and 60. So is it 100? Let's see. Yeah, it's 100 degrees. So we found this missing angle here is 100, which makes the missing arc across from it 100. So remember, if it's a central angle, then they're equal. If it's not a central angle, then you can't use this theorem. We'll see what happens later with that. All right, QRS is this arc here on the outside. Well, they're all on the outside. QRS. And we're going to add up those angle measures, 160, right? 100 plus 60. So that makes the corresponding arc measure the same, 160. So the measure of QRS is 160 degrees. So you can see sometimes you can pull the angle measure right off the diagram, and sometimes you have to solve for it. Think about it. How are you feeling about circles so far? You think, hey, I think I'm really going to like this unit. I really like this unit because I'm visual. Or B, I just want to eat things that are circular in shape. Or you'll get through this fine, but you're just not sure you'll like it. Either way, I want you guys to know that I'm here to help you through this unit. It is going to be sort of definition theorem heavy, so we are going to have to sort of keep track of all those different rules. Here's one. What about the converse of the central angle theorem? So remember from back in the day when we did logic, the word converse. What does the word converse mean? It means the reverse, right? So we know in the central angle theorem, if the angle is in the center, the arc across from it is equal, right? Well, the converse tells us the opposite. So here we know the arc measures. See how the outside of the circle is labeled? So then we're going to immediately know the angle measure as well. So if this arc is 154, the angle across from it that's on the center is 154. Same here. If this QU is 86, then the angle on the inside of that circle is 86. Only because it's a central angle. Here this is 60, so this one is 60. Now it wants us to find SPQ. So let's label what they want us to find. Where's P? Oh, there is no P. Oh, it's on the inside. I see it. I covered it up. SPQ. There we go. P is the center of that angle. Center of that circle. So they want us to find S to P to Q. So let's just find the whole circle. Because here, these little red tick marks inside of the circle here, that tells you that those are equal. Remember in triangles, we have tick marks that tell us which angles match up. The same thing works in circles. So those two are equal. They have the same amount of tick marks. If they each had 2, they would be equal, right? So let's find them. We know there's already 86 plus 154 plus 60 degrees. There's already that many degrees marked. Let's see, what's that total? So that'd be 60. Is that 300? I believe. I just did that in my head. I don't have a calculator handy. I'm sure you guys can double check. Let's see. Let me double check because I don't want to mess anybody up. Yep. Wait. 300 or 200? 300. Yep, I was right. Okay, good. So we have 300 degrees already being used in the circle. And we know there's a total of 360, right? So let's see how many degrees are left. 60 degrees left to use up for our angles. And we know those two angles have to be equal. So they must each be 30 degrees. So we found each of these is 30. So if we're going to look at the yellow angle this way, didn't really tell us, then we're going to add up 86 plus 30 plus 30, right? So is that 146? That's what we're going to go with for the angle SPQ. This question's kind of ambiguous, is that the right word? Because we could technically be thinking about SPQ this way. So I just made that decision for us. If it's in your OMHS, it will definitely be more clear. I made this problem up. I should have been more clear about that. All right, let's try one like this. So given AD is the diameter, there we go again, it tells us AD is the diameter, find the value of X, Y, and Z. So this might be a really good time for you guys to press pause, try this on your own, and then come back for the answer. So just to be clear, angle X here, I'm talking about the angle inside. Angle Y is talking about the angle inside. And angle Z is talking about this arc measure. Okay, so there's the different measures there, right? So angle X, remember this is a central angle. It's coming from the center O. They're equal to the arc measures across from them. So we have 25 labeled here. So that means X is going to be 25. All right, and then 55 degrees is across from Z. So Z is going to be 55. So the only thing left to find is Y. And we know that the entire thing is what? Did they tell us this is the diameter? So how many degrees total in half this circle, right? Because the diameter cuts a circle in half. So that's why this is so important. It is 180 degrees. So we know this is going to total 180. So we just need to find what's missing, right? 180 minus 25 minus 55. So it's 100, right? So Y is 100 degrees. All right, don't forget to watch the recordings on your plan for Tuesday and Thursday of this week and complete the corresponding required USA test prep assignment. We do not have classes on Friday, so this assignment will be available for you on Thursday of this week. Per your email that I sent, don't forget to stop into Classic hours if you want to. The practice is required. You will get points for doing that, but you don't have to come during this time slot. It's only if you want to be able to, have me check your work and all of that. So if you guys need anything, don't forget I am here via email and wanting to help you guys out, and we will hopefully get back to normal next week. Bye, everybody.